This media was gratuitously produced by Clear Contributions Audio Video. The intellectual property contained within belongs to Dr. Barbara Van Kyken. Clear Contributions. Let's have clarity.
All right. So let's look at the review for the test, and we can start off by an example with a bromine. Just a minute. I have so many documents in here now. Okay, good. I think I have an example towards the end of this or not. All right, we'll make one up. I'll put it at the end. You might have an example at the end of the problem 13 in the workbook chapter for 6, because I know we've worked a problem like this. I just can't place where it is, but there you go. So the idea is anytime you create a carbocation or carbon radical, because it's electron deficient, anything you can do to get electrons to it is going to help it. And so the two of the things that you sort of learned in this chapter is if you have bonds next door that can overlap the empty p orbital and stabilize it, or if you have non-bonded electrons, that orbital can actually overlap and share. So either of those are resources for it. So when you're trying to figure out how to label everything, if you have a secondary and a secondary, but one of them has an atom with adjacent non-bonded electrons, that's going to be a stabilizing factor. And so that would be a better secondary. So you'd want to put the carbocation on this carbon. Pi bond's the most reactive feature. You're still going to then look for something electron deficient. The electrons go towards electron deficient. In other words, they're going towards a partial positive or an incomplete valence shell. Check the atom that the electrons went to make sure it's okay. If not, it has to let go of electrons from a bond. Okay, and I'm going to draw out the molecule so far, but it's not going to be totally correct. I just want to kind of help you picture and a little better. So we're going to fix this in a minute. So you would have that sort of. But you're not going to let the carbocation develop completely as long as you have the non-bonded electrons there. So although I've drawn this out as 2 steps, it doesn't really occur as 2 steps. It all occurs simultaneously, so I'll go back and fix it in a minute. But you would have this sharing electrons with that to form a double bond there, so that it doesn't have to have a carbocation. So like I said, that's not technically correct the way I did it. I just wanted to dissect it out for you. So anyway, that shares in that step, and you never have a carbocation there, which means that you're not going to have a shift or anything because it never really fully formed. But you can think of it the same way as you would a carbocation, because you still have a partial positive charge on the carbon, since chlorine is more electronegative. And the chlorine has a partial negative, but it also has a positive formal charge because it has too many bonds. So that partial negative and positive formal charge is not a good combination. So it's going to want to do something about it. So you still will take something that's electron rich, like the bromine and its electron pair, and react it with a carbon to give it a 4th bond so that it doesn't have to walk around with that double bond there all the time. So you treat it the same way as a carbocation, it's just that you have a stabilization feature in the middle there. So quite often I've had students who kind of buck at this idea because they feel like, well, chlorine is electronegative, so it would be withdrawing electrons, and so that would destabilize a carbocation. But the fact that it has non-bonded electrons that it can actually share is a more important feature for it. I also have students who are kind of like upset because if chlorine is that electronegative, why would it want to have a positive formal charge? And it doesn't, but if you have something that has 8 electrons around it, that's a whole lot more stable than something with a positive formal charge. So although this isn't great, and that's why you're going to react it again, it still is better than having a carbocation where you don't have a complete octet.
So do you need to show that out, or can you just know that happens with the bromine on the carbon that has the other more stable?
Is the chlorine? Yeah. So actually, now that you've asked the question, I'll go through the test with you and show you what I'm expecting for each type of question. I didn't have it so that you're not going to have to show arrows, products, and stereochemistry all in one problem, because it creates too many layers for the grading, because if you mess one thing up and then you mess everything else up after that, that's, it's kind of difficult to see where you went wrong and to grade it fairly. The other thing is, if I keep grading arrows every time, then I'm grading the same thing like 50 times down the page, when I really just needed to see if you knew how to do it or not once. So I've got that broken out. It's helpful if you know how everything works so you can predict the product, but I only have one standalone question where I ask you to put arrows in. And I'll show you how that works. And we'll go through the problems through a couple of these for you. Because I know there's a few things on here that you've been doing all along and you know the answer, but you just don't realize that you do. So I just wanted to help you put it into words. But anyway, I wanted you to know what the 3 stabilization strategies are for a carbocation or carbon radical. Well, 3 for a carbocation. How to select which vanillic carbon will become the carbocation or carbon radical. How to label, because we're also incorporating chapter 5 in this. So I wanted you to make a list of the 6 types of labels and then apply them. Then this is a question for you showing me if you know how to use reaction mechanism arrows. You notice I have the reactants and then the products. You also notice that I've got the exact reactions that you're doing in this chapter. So, for instance, if you're going to create a carbocation by having the pi bond go to something electron deficient and then resolving the carbocation, or if you're going to, and I goofed this up, sorry, you can change it on yours. If you're going to have a reaction that involves a radical. And then this is kind of the putting it together. Tell me what the product is for a reaction and the stereochemistry, and I will have the stereochemistry written out for you. So you just have to circle it, and you don't have to have any kind of questions about is R/S and R/S okay, or do you want RRRS, or do you want 4 possibilities, or do you want, okay, just pick. So because in this chapter, you're going from a double bond to all single bonds, you're only looking at whether there is R or S, and so the only answer choices you could possibly have would be none, R and S, or all 4. The other possibilities that are written in here are going to be for later chapters where you might be left with a double bond at the end of a reaction. But anyway, you'll circle one of those, whatever applies. I'm afraid that when I went through and worked the problems in this, I was trying to just randomly come up with problems that are different from the ones that I wrote for the test. And so I was just kind of like coming up with things out of my head. Oh, maybe a shift with a ring. Oh, maybe and I was coming up with different ones. And I realized, though, that when I worked through these, almost none of them have a chirality center. So, but I'm sure that you know that if there's one chirality center, it's R and S, and if there's 2 that you've created, then it's all 4 possibilities. So I'm sorry about that. I didn't do a good job with that part. And then there will be one or two questions on the test, and it'll only be worth about 10%, but I want to make sure that you don't forget the stuff that we did previously. I'm trying to help you keep all of this information together and do well on the comprehensive final. So anyway, I've got an example here with mixed IUPAC versus pure IUPAC. So that's chapter 4 and a little bit of chapter 3. And then I also have the common name and IUPAC name for those molecules, which is chapters 1 and 3. And oh yeah, by the way, this has a chirality center in it, so that also incorporates chapter 2. So I tried to come up with something that would help you review all of the chapters and make sure you don't forget that stuff. All right, the test will be pretty much the same exact format. It won't be the same exact questions, but it's going to have those same exact types of questions where I have you show me the arrows, I have you label things, I have you make these lists, and so on. So we'll go over it in more detail tomorrow during the review, but I thought I would get you started anyway on the 3 different stabilization strategies that you know so far for a carbocation. I'm going to show you 2 more for the semester, and that's pretty much got it. So now if I can get you to just train in on, I got a carbocation, what are my resources here, then you understand all of the reactions. So what stabilization strategies do you have if something starts to develop a carbocation? In other words, what is telling you about where carbocation would start to develop because you have stabilization going on? What do you think?
Hydrogen shift.
Okay, you might have a shift to make it better, to put it in a better location. And so that could be an alkyl shift or a hydride shift, no matter, depending on what the situation is. What are the other 2? No. It's what? The overlapping with the non-bonded pairs that I just showed you. And the other one is the one that you're doing all the time, and so this has just become second nature and you don't even realize. I think. Yeah, whether it's tertiary, secondary, primary. In other words, if you're overlapping with bonds that are next door. Those are all resources for electrons. Okay, so this is now in totally backwards order from the way that you gave them to me, but so the hyperconjugation is where you're saying, is this tertiary or is it secondary or is it primary? Whoop, primary. Yeah. And that's because if you have carbons next door, the bonds can overlap with the electron deficient p orbital. That stabilizes it. The overlap with non-bonded electrons is the same thing, except for instead of having a line coming off here, you have an orbital with electron pairs in it. And then if you can do a shift. The next chapter, I'll show you how to use a resource from 2 atoms away, and the chapter after that is electron resources from farther away. And the farther away is where you're lining up a whole bunch of p orbitals so that you can shuttle electrons down this little track. Okay, so those are features you want to look for. All right, and so you can already see on the next one, since I can't scroll any farther to make that go off screen, when you're selecting the vinylic carbon that would be better at developing a carbocation or carbon radical, you're looking at those 3 different stabilization features. And so since the hyperconjugation, you're looking at tertiary, secondary, primary, that one is pretty easy for you. But then for B and C that I have here with overlapping non-bonded pairs or shifts, then you're looking at the notations that I was showing you, like where you have secondary with a possibility for a shift, or a secondary with a non-bonded electron pair next to it.
So if you had that situation where you had a second degree with a shift and then a second degree with a non-bonded electron, which one would be better to bring?
Ooh, I'm not going to do that to you, but I would say that the non-bonded electron pair, because then you don't have a carbocation at all.
Okay.
Yep. That's a great question. All right, but you can do BC and whatever else is left on that page for the vinylic carbons, and we can go over that. And as a PS, do you guys want hard copy or airdrop? And I'm not going to make you decide that the whole class has to do one or the other, but I'm just saying how many of you want a hard copy so I know how many to make up.
Which one's easier for you?
I don't care. Hard copy? The test. Hard copy? Okay.
Oh, yeah, on the test, yeah.
Okay, perfect. So now, unfortunately, my A, B, and C are different from yours, but all I was doing was matching it up to one of the 3 stabilization features that we listed in question 1. Stabilizing an incomplete valence shell. Since an incomplete valence shell is so crazy reactive and unstable, that's the whole game. And so that's why I want you to get good at focusing on this, because this is really the whole basis for the reaction. Do you have any questions or anything that doesn't match up or anything? On the first one I put hyperconjugation. It's still a long word, but it's a lot easier than writing out overlap of bonds with the p orbital, the electron deficient p orbital. But if you wanted to explain that instead of writing hyperconjugation, that's fine. It's just that's the term for it. Overlap of bonds with an electron deficient p orbital. No, because the group that you're shifting has to be right next door, because you have to overlap the bond so it can shift over. And you notice that this is 2 away. It's like if you put those, so this is 4, yeah, but you'd have to jump over, and you can't do that. Yeah. So here, maybe that helps if I draw that in. And then the last thing before you leave, for question 3, I just wanted you to kind of see or remind you what the different labels are. You have these in your notes hopefully a bajillion times by now. But an incomplete valence shell, you know it's that if you have a carbocation, which it means a carbon with 3 bonds and no extra electrons, or no additional electrons, or a carbon radical, which will have 3 bonds and a dot, or any other kind of atom that has a dot associated with it. You haven't seen the strained ring yet. You will see that in chapter 7, so you don't have to work with it. I just have that on your list for right now, so you keep it in mind. These are in order of decreasing reactivity, so a pi bond is going to be loosely held electrons, but it's not incredibly unstable, so that's next on the list. The high concentration doesn't necessarily affect reactivity, but if you have something that is really reactive, that's an important feature. And then you have partial positives and negatives mean you have a difference in electronegativity. Positives and negatives mean that you don't have the right number of bonds as long as you have a complete valence shell. So those are telling you 2 different aspects usually of the atom. Both of them have to be taken care of, and so they are kind of separate features but along the same order of reactivity. And then the last one is not reactive, and that's why you're crossing it off. If you have bonds that are too strong, which means that you have bonds between atoms that only have 1 or 2 shells each. Those are going to be small atoms, so they form a short bond, and that will be way too crazy strong. So you can't do anything if one of the atoms has to let go of that bond in order to react. Because hydrogen can only form 1 bond, it has to let go of the bond to be able to form a new one, and so that's one of the reasons why we're crossing that off. And then carbon also would have 4 bonds to begin with. It can't have more than that, so it would also have to let go. All right, so for tomorrow, your homework is fill in the rest of this, and we'll go over it and see where you have weaknesses and see if there's anything else that I need to prepare for you to help you review for the test on Wednesday. Okay, and also if I know several of you have missed quite a bit of class for illness or other kinds of things, and so if you have particular questions or basics that you want me to go over, bring those with you, and I can after we've gone through this worksheet, then I can stay behind and go back over some of the stuff from the concept section of the chapter. All right.